A heap is a binary tree that is complete and has the property that the parent node should be greater than or equal to the children nodes if it is a max heap. So there are two types of heaps, max heap and min heap. In the max heap, the parent node should be greater than or equal to the children nodes. And in the case, for example, here 30 is greater than 20 and 25, 20 is greater than 10 and 15, 10 is greater than 8 and 5, 15 is greater than 7, 25 is greater than 12 and 17. So this is a max heap. So it is a complete, all the child nodes above this leaf node are full, like this complete binary tree. This root node can have at most 2 children, and it has 2 children in fact. And the 20 is also full of nodes. It can have at most 2 children, and this 25 can have at most 2 children. But the leaf nodes can be 0, 1 or 2. So this is a max heap. In the case of a min heap, the parent node should be smaller than or equal to the children nodes. So this is a min heap. So 5 is smaller than 8 and 7. 8 is smaller than 10, 15. 7 is smaller than 12 and 17. 10 is smaller than 20, 25. So this is a min heap. Now let us see how we can insert a node into a heap. Inserting a node into a heap, to a min heap, first we need to go to the leaf nodes, then traverse from left to the rightmost leaf node. And then after the rightmost leaf node, we insert the value. Then we insert the new node. So if an inserted element is smaller than the parent node's key, then we swap the value with the parent key until all the nodes are at correct location. Let us see an example. So in this min heap, we want to add 4. So first we need to go to the leaf nodes, go down until we have leaf nodes. So we reach to the leaf nodes, and then we traverse from left to the right. So left 20, then to the right. So rightmost child is 25. So after 25, we need to see if there is a sibling or no. If there is no sibling, so that means if the parent node has all the children, means if it has 2 children, then we need to check its sibling. So in this case, 4 can be attached to 15. But one thing we can see here that 4 is smaller than 15, and we are working with the min heap, so we need to swap these values. After this, again 4 is smaller than 8, then again we need to swap the value, and then so here 8 and 4 are swapped, and then again 4 is smaller than 5, so again we need to swap. So 4 should come here, 5 should come here. So 4 comes here, 5 comes here. Now again we need to check whether it violates the heap property or no. So 4 is smaller than 5 and 7, 5 is smaller than 10 and 8, 10 is smaller than 20, 25, 8 is smaller than 15, and 7 is smaller than 12 and 17. So all this is min heap. Similar to this, we can insert a node into a max heap. So what we can do, we again need to go to the rightmost child node, leaf node, and then add the new node. And then if it violates the heap property, then we swap the nodes, the values until all the nodes are at correct location. So how we can delete a node from a heap? So to delete the root node of a heap, we first swap it with the rightmost leaf node. And after the swap, if it violates the heap property, first we delete the leaf node and after the swap, and if it violates the heap property, then we restructure the tree. I'm saying it's a tree because if it violates the heap property, it will not be a heap. So it will be a binary tree. So now let us take an example of this mean heap. In this mean heap, the two leaf nodes are 20 and 25. In the given heap, 20, 25 are the leaf nodes, and the rightmost leaf node in this case is 25. So now we swap 25 with 4, and then we delete 4. So after deleting 4, we obtain this heap, this binary tree actually. So 25 is the root node here, but as we are working with the mean heap, it is not at a correct location. So it is violating the heap property. So now we need to swap this 5 with 8. We need to swap. So we need to swap 5 and 25 and 25. So after swapping, we will obtain this one. So this is after swap. Again, 25 is not at correct location, so we swap 25 is greater than 8, so we swap it with 8. And after this, 25 comes here, 8 comes here, 5. So now 5 is smaller than 8 and 7, 8 is smaller than 10 and 25, 7 is smaller than 12 and 17, and 10 is smaller than 20. So this is a mean heap. Okay, similar to this, we can delete a node from a max heap also. So now let us see what is a heap construction. So a heap can be constructed from the elements of an array. So if you are given an array, you can construct a heap. We can do it through two approaches. One is called top-down approach, another is called bottom-up approach. So let us assume that the root node has height 0 and the children of the root node have height 1 and their children have height 2 and so on. So we are starting from the root, then as height 0, the child node has height 1, and then we go down. So how we can calculate the height of a heap? So we take a floor function of log 2n, where n is the number of elements in the array. So if n is 7, then we can find the floor of log 27. The log 27 is 2.8, so floor value of 2.8 is 2. So height of the tree is 2. So we'll follow the convention that the root node we denote of height 0, then its child node as height 1, and then its child node as height 2. The children's children are at height 2. So bottom up heap construction. In the bottom up heap construction, we start from the leaf node. Then we move one level up and compare the keys and swap it if it violates the heap property. And then we move one level up and compare the keys and swap if it violates the heap property. And we do it until we reach the leaf node. This process is called heapification. So So these are the steps. So suppose the array has n elements, then first we can find out the height of the array using the log2n floor function. Okay, from here we can find the height of the array, and then we calculate, because we are working with the leaf nodes, we first plot the leaf nodes. So we need to find out the number of leaf nodes. So we can find the number of leaf nodes at n minus 2 to the power h plus 1. N is the number of elements in the array. H is the height of the tree, which can be means the heap, which can be constructed from the array, and we take 2 to the power h of that, and then we add 1. For k equal to 1, 2, 3, 4, and so on, we calculate the number of upper level nodes by 2 to the power h by 2 to the power k. We take first k equal to 1, then k equal to 2, k equal to 3, until we reach the root node. The root node will be 2 to the power h by 2 to the power k equal to 1. So because the root node will be just 1, so when this goes to 1, we'll stop. So first we fill the leaf nodes, then we go one level up and fill these nodes, then we go one level up. So this will be our next level. This will be our leaf nodes. So based on the number of elements in each level, the elements from array are taken. The leaf nodes are the last elements of the array, then the level 1, and so on. The root element is at index 0. So as we already saw, so height we consider this as 0, then 1, then at 2, and so on. So now let us take an example how to construct a heap from an array. So we have an array A which has elements 2, 5, 11, 19, 12, 13, 15, 17, 1, and we create a mean heap from this array. So first we need to find out, so how many elements are there? So there are 9 elements in this. So first we can find out the height of the heap. So height is log 2n. Log 2n is 3.17 a floor. If we take the floor of that, so it will be 3. So number of leaf nodes of this heap will be 9 minus 2 to the power 3 plus 1 equal to 9 minus 8 plus 1 is 2. The leaf nodes are the last 2 elements. So there are 2 leaf nodes in this. So we will work with these last elements. So again notice that 17 will be the first left node, and then 1 will be the right node. Then we start filling from left to right. And then because this is a leaf node, we don't have anything to swap. So 17 and 1. So because we'll be working with 9 nodes, so we have constructed this heap, and the other elements will fill when we progress. So 17 and 1 are the leaf nodes. After that, we will go one level up. For this level, we find out 2 to the power h by 2 to the power k. Here k will be 1. For this one, 2 to the power h by 2 to the power k. Here k will be 2. For this one, 2 to the power h by 2 to the power k. K will be 3 here. So h, because already we saw h is 3. So in this case, 2 to the power 3 by 2, 4. How many nodes we need? 4 nodes. In this case, 2 to the power 3 by 2 to the power 2. 8 by 4 is 2. In this case, 2 to the power 3 by 2 to the power 3, 1. So this is the root node. So after 7, means before 17, we will check 4 elements in the array. So before 17, we have these 4 elements. So our 4 elements are, suppose we denote by this. So our 4 elements are 19, 12, 13, 11. So 19, 12, 13, 11. So we have 19, 12, 13, 11. So we'll fill 19, 12, 13. Sorry, here. We'll fill 19, 12, 13, 15. Okay. So we have 15 or 11? 15. Yes. It's no mistake. So we have 19, 12, 13, 15. So now we compare and see if it violates the heap property or no. So here 1 is the right child of 19. It is violating because we are considering we are working with the min heap. So we need to swap these values. So we will have this. So 1 will be the parent node, 19 will be its child node. Here we don't need to swap anything. So because it does not have any parent node. So after this, to fill this level, what we need to do? We need to increase k. K will become 2 here. So 2 to the power 3 by 4. So it will be 2. So 2 nodes for this level. Now, before 15, we need to take 2 more nodes, 2 more elements of the array. And those elements are 5 and 11. So we will fill 5 first and then 11. So we filled this one also. Now we need to check whether it violates the heap property or no. So yes, it violates. So 11 is smaller than 5, but it is its left child. And we are working with the min heap, so they should swap. So we are swapping this value. So this 1 and 5 should swap. So 1 has come here and 5 has come here. Now we see if it violates the heap property or no. So no, it is fine. So this 5 is also fine, 11 is also fine. So number of nodes in the upper level to the nodes in 4 will be this. So now we will work with the root node. So this is the root node. So now this will be the first element of the array. So our first element of the array is 2. So now we see that 1 and 2 should swap because it is violating the heap property. So 1 will come here and 2 should go here. So 1 will be the root node and 2 and 11. Now we see if it is violating the heap property or no. So no, all are fine. So bottom up heap construction has time complexity of O(n). For top down heap construction, this is much easier. And we start from the root node. So the first element of the array will be the root node. Then its two elements will be its children nodes. Then 4 elements, then 8 elements, and so on. So to find out the left child of a parent node I, we denote it by 2i plus 1, and the right child will be 2i plus 2. So for this one, the I is 0. So 0 times this left child will be 0 times 2 plus 1 is 1. So at index 1, this will be the left child will be there. For the element at index 2 will be placed to the right child because 2 times 0 plus 2 will be 2. Similarly, for this one, I is 1. So 2 times 1 plus 1 is 3. This is 2 times 1 plus 2 is 4. This is 5 and then 6 and so on we can find out. So let us work with this. These are 16, 15, 14, 13, 12, 11. So we are considering the sorted array because we already saw how to swap the values, so we can just fill the values. So first we'll start with the root node. So 16 is the root node. Its left child will be at index 1, right child will be at index 2. So 15 will be left, 14 will be its right child. Then for 15, because this is I equal to 1, this will be 2i plus 1. 2i is 2 plus 1, 3. So the 15's left child will be at index 3. It is 13. 15 right child will be at index 2i plus 2. 2 plus 2 is 4 at index 4. It is 12. and then 14th left child will be at index. Here I is 2, so 2i plus 1. 2i plus 1, 2 to 4, 1, 5. This is 11. And because there is no element after this, it will not have any right child. So what is a heap sort? Similar to the insertion sort, merge sort, quick sort, bubble sort, selection sort, we have a heap sort. So suppose we have an array, so we need to sort this array. So first we can construct a heap, and then we keep deleting the root node until all the nodes are deleted. So heap sort is a sorting technique, as you know, to sort any array or sequence of elements. To sort an array, a sequence by heap sort, we follow these steps. First, we construct a heap from the given array. It can be a max heap or min heap. So one thing we can notice that if you are creating a max heap and keep deleting the root node, then it will provide a sorted sequence in increasing order. If we create a min heap, it will provide a sorted sequence in decreasing order. I'm saying decreasing and increasing in the sense that will just because we'll swap with the last element of the array. So the max heap will be this is the largest element, greatest element of the array, and then it will keep decreasing. So in this, from a start to end, it will be increasing order in the max heap, but in the case of min heap, it will be decreasing. It will be in the decreasing order. So we keep deleting the root nodes and restructure the boundary tree if it violates the heap property to obtain a heap, and we'll keep repeating this, deleting the root node and restructure the heap until all the nodes are deleted and we obtain a sorted array. So let us take an example. Let array A equal to 12, 5, 11, 18, 32. I took a small number so that we can do the sorting faster. But you can take a big numbers. The process will follow the same. You need to follow the same process. So you can sort this by a heap sort. First, what we need to do, we need to construct the max heap from the array. In this example, we are constructing a max heap, but you can also work with a min heap, but your sorted array will be in decreasing order. So you can construct this using the bottom-up approach or top-down approach. Top-down approach will be a little bit slower than the bottom-up approach. So let us check it with the top-down approach, because that is much easier to show it here. So 32 will be the root node. Then 11 to 18, 11 will be its children nodes. Then 12, 15 will be the children node of 18. If there is any other element, then it will become the child node of 11. But because we have just 5 elements, this will be our heap. So 32 is now because we are considering the heap node, we need to check the heap property also. So 32 is greater than 18, that is fine. 32 is greater than 11, it is good. 18 is greater than 12, and it is greater than 5. So we have a sorted array. So no, means after swapping, we have obtained this. So you can, when you create a heap from this, you can get 12, then 5, then 11, then 18, then 32. Then you need to keep swapping until you obtain a heap. So this is our final heap. And because already we have shown how to create a heap, we don't need to show it again here. So 32 is the root node. Now to delete the root node, what we need to do? We need to swap it with the rightmost leaf node. So in this case, 5 is the rightmost leaf node. So we swap 32 and 5. After that, we delete 32. So 5 and 32 are swapped. 32 comes here, 5 comes here. Then we can delete this. I have marked this, which is mark the 32 in red. So we don't need to repeat this one. So now 5 is smaller than 18 and 5 is smaller than 11 and 18 is greater than 12. So this one is fine, but 5 is smaller than 18. So we need to swap to make a heap. So 18 will come here and 5 will go and become its child node. So 5 and 12. So 5 is smaller than 12. So again, we need to swap because we are working with a max heap. So 12 will become the child node of 18 and 5 will become the child node of 12. So we obtain this heap. Now we need to delete this to 18. What we need to do? We need to go and check the leaf node. And the rightmost leaf node, in fact, there is just one leaf node. So we need to swap 18 and 5. So 5 and 18 will be swapped. So again, 5 and 18. In this case, 18 was here. So 18 and 5 are swapped. So in the array, we can write 5, 12, 11, 18, 32. Now we have 3 elements in the heap, 5, 12, and 11. So again, this is not, it is violating the heap property. So we need to swap 12 and 5. So 12 will be here, 5 will be its child node. But we need to delete this 12 now, the root node. So again, we need to swap it with the rightmost child node. Here, the rightmost child node is 11. So we need to swap 11 and 12. So 11 will become the root node and 12 will become its child node. So we can delete 12. So after swapping, we have obtained here 11 and 12 are swapped. So 12. So after deleting 12, we obtain this heap where the root node is 11, the child node is 5. This is again the max heap, so we don't need to do anything. Now we need to delete 11. So we can swap it with 5. So 5 will become the root node, 11 will become its child node. And then we can delete 11. So we have swapped 11 and 5. So 11 comes here, the array will become 5, 11, 12, 13, 18, 11, 12, 18, 32 are already sorted. So now we have just one element, 5. So because there is just one element, it is sorted. So we have obtained a sorted array 5, 11, 12, 18, 32.